Yes guys, so in this video we are going to discuss about hysteresis losses, hysteresis loop. Generally, what is the definition of hysteresis losses? Hysteresis losses nothing but the losses due to magnetic reversal, or the losses during the magnetic reversal, not due to, for example, the losses during the magnetic reversal, especially due to magnetic inertia, or residual flux or retentivity, all the things. Just keep it here. Hysteresis losses nothing but the losses during the magnetic reversal due to magnetic inertia of the transformer core, magnetic inertia of the core. Generally, let's see here, for example, I am giving a AC supply to the transformer. I am giving AC supply to the transformer, for example, like this. This AC supply given to the transformer, nothing but, see here the flux is 0 initially, from 0 to maximum, then after maximum to 0, then after 0 to negative maximum, again to the 0, again to the 0. Here 0 to maximum nothing but magnetization. Again maximum to 0 nothing but demagnetization. Again 0 to negative maximum nothing but reverse magnetization. This is called reverse magnetization. Again negative maximum to 0 nothing but reverse demagnetization. Reverse demagnetization. This is what generally the AC supply given to the transformer. Nothing but, this is nothing but the magnetic reversal. What is going on here? The magnetic reversal is going on here. Here, initially, when the magnetization takes place, initially, up to saturation, the magnetic flux density also increases. This is called hysteresis loop. Hysteresis loop nothing but BH loop. Hysteresis loop nothing but BH loop. Let's have a look at this hysteresis loop. Initially, from 0 to maximum, which is called magnetization, nothing but, see here, the magnetization will be takes place here. After the magnetization, again we need this demagnetization. During this demagnetization, actually the flux not goes straightly to the 0. The flux not goes straightly to the 0. How it will goes? See here, it is decreases from maximum to 0 through this curve, not straightly. If magnetization and demagnetization is a straight curve, nothing but hysteresis losses 0 actually. If the magnetization and demagnetization is a straight curve, then the hysteresis losses 0. Generally, this is not possible. This is the ideal case. Generally, in air core transformers, we may have this. But practically, this is the magnetization curve and this is the demagnetization curve. During demagnetization, the flux density will be struck here. The flux density will be struck here. It not goes to 0 actually. It is struck here. Why it is struck here? Due to residual magnetism. This is called residual magnetism, and this property is called retentivity. Retentivity nothing but the property which opposes the flux density, which is not goes to 0. Retentivity nothing but the flux density is not goes to 0, even though the intensity, the magnetization force is 0. Even though magnetization force is 0, but the flux density not 0. practically the magnetization force we can represent with magnetizing current. When the magnetizing current increases, the flux density also increases. When again the magnetizing current comes to zero, even though magnetizing current comes to zero, but the flux density not zero. But the flux density not zero. When the flux density not zero, that phenomenon is called retentivity. But we need that again reverse magnetization. To get reverse magnetization, to start reverse magnetization, now we have to be it from the zero state. So we need to bring this flux density to zero. To bring this flux density to zero, to avoid this residual flux, residual magnetism, to overcome this retentivity phenomena, we need to apply some extra force in reverse direction, some extra magnetizing current in reverse direction. This extra magnetizing current in reverse direction, this extra force is called coercivity. Of course, IMU 0, flux density not 0. That's why I am applying some extra force in reverse direction. This is in reverse direction. This is called reverse magnetization force. This is called coercivity. When coercivity applied, then the flux density comes to 0. Then the flux density comes to 0. Now we are at 0 flux and 0 flux density. Again, we need in magnetization in reverse direction. This is the reverse magnetization. This is the reverse magnetization. After saturation, again, we need reverse demagnetization. Actually, it not follows the same curve. Due to magnetic inertia, it tries to goes to zero in next way. But the flux density not goes to zero. This phenomenon is called retentivity. Even though magnetizing current is zero, even though magnetizing force is zero, but the flux density not zero. This is called retentivity. To overcome this retentivity, to overcome this residual flux, we need to apply some extra force in opposite direction. We need to apply some extra force in opposite direction, which is called coercive force. Coercivity. When coercivity applied, then the flux density comes to zero. Again, the next cycle will be started here. So what happens are here? Once have a look here. Generally, this is the flux density. This is the flux intensity. Flux intensity are magnetizing force or magnetizing current. When I mu 0, the flux density is 0. When I mu increases, the flux density also increases. Then after this is called magnetization, and demagnetization will be tries to comes to flux density 0, but it is not possible due to residual magnetism, residual flux. This phenomenon is called retentivity. To overcome retentivity, we need to apply some extra force in opposite direction, which is called coercive force. When coercive force applied, then the flux density goes to 0. Again, in reverse demagnetization, this is the reverse demagnetization. Now it has to goes to 0 again, but due to residual flux, again it not goes to 0. Due to residual flux, it not goes to 0. Again, we need to apply some extra force. Now, when the coercive force applied in opposite direction, then flux density comes to 0. This is called coercive curve, hysteresis curve. Okay, so this complete hysteresis curve I shown here. This complete hysteresis curve I shown here already. See here, this is the magnetization. This is the magnetization, and this is the demagnetization, and this is the reverse magnetization, and this is the reverse demagnetization. This complete curve is called hysteresis curve. Okay guys, and this portion is called retentivity or residual flux. Retentivity. The units of retentivity, nothing but indirectly flux density. The units of retentivity, Weber per meter square or Tesla. Again, this is the coercive force, nothing but intensity or magnetic field strength or magnetizing force. and this is also magnetizing force in reverse direction. This is also retentivity or residual flux. Residual flux nothing but, can you tell me what is residual flux? Even though the current in the magnetic circuit is zero, even though the current in the magnetic circuit is zero, here some magnetic flux density will be there. I mu 0, but some flux density will be there. That is called, some flux will be there. That flux is called residual flux. That flux density is called retentivity here. To overcome retentivity, we need to apply some extra force in reverse direction. That is called coercive force or coercivity. This is called BH curve or hysteresis curve. The BH curve is linear for air core transformer. And here the thing is that, what is hysteresis losses from this curve? From this curve, the area of BH curve is equals to hysteresis losses. The area of BH curve is equals to hysteresis losses. This is the thing. Sometimes they may ask you the height of the BH curve decided by, the height of the BH curve decided by flux density. The width of the BH curve decided by, can you tell me, the width of the BH curve decided by core volume, the volume of the core, the width of the BH curve decided by core volume. Where the area nothing but, where the hysteresis losses is nothing but area, right? Area nothing but x-axis into y-axis, right? So the y-axis nothing but flux density, maximum flux density whole power of x. X is a hysteresis coefficient. X is a hysteresis coefficient. Y-axis and x-axis is the volume. X-axis is the volume. This is the area of this curve. And here some constant, neta is a Steinmetz constant. Some constant, neta is the Steinmetz constant. I B max whole power x and volume V. This is area of one curve. But the number of loops are decided by, number of loops are decided by number of cycles. Number of cycles decided by frequency. Number of cycles decided by frequency. So for a 50 hedges, 50 cycles. For 60 hedges, 60 cycles. We need to calculate for all the cycles. This is the hysteresis losses. So what is the formula for hysteresis losses? The hysteresis losses formula, Steinmetz constant into B max whole power x into volume of the core into the frequency. This is hysteresis losses. Okay guys, the hysteresis losses depends on flux density, volume of the core and frequency. So how we can reduce this hysteresis losses? Yes, by selecting this x. What is this x? X is the hysteresis coefficient. Hysteresis coefficient. In generally, the x value 1.5 to 2.5. 1.5 to 2.5. Mild steel, mild iron, silicon steel, CRGO silicon steel. For those values, it will be vary from 1.5 to 2.5. In generally, if the x value decreases, if we control this x value, ultimately the hysteresis losses also reduces. So for which material x value is minimum? Yes, for CRGO silicon steel, or simply for silicon steel, the x value is very minimum. How much it is? Its value just 1.6. That's why the transformer core made up of silicon steel, because for silicon steel the hysteresis coefficient is minimum. How much? Just 1.6. Just 1.6. That's why by using silicon steel we can construct our transformer core. This is simply what about hysteresis losses and hysteresis curve. Hysteresis losses nothing but during the magnetic reversal, the losses due to magnetic inertia. Due to the magnetic inertia, it is shifted from actual position to another position. Actual way to another way. The magnetic inertia result is the retentivity, residual flux actually. This is simply what about hysteresis losses. What is hysteresis losses? And we can reduce. How we can reduce them? By using silicon steel material, we can reduce the hysteresis losses. For silicon steel material, X value just 1.6. Are you clear guys?